Now we are pointing to M74, that is a spiral galaxy, a very nice object because it's a face-on galaxy, as you can see here in the web.
But you haven't taken this picture?
No.
This isn't your picture?
No.
How are you going to take your picture?
Well, now, of course, we will put some broadband filters and we will obtain a grayscale image.
What we have here is a composite image, which means it's several filters of M74. It's most of the galaxy shown here. It extends slightly beyond this frame. These pinky regions here are nebulae, and this is the places in M74 where those newborn stars are forming. What I like about it is it's a beautiful star-forming galaxy. It's got a distance about 30 million light years away, so it's sort of one of the furthest Messier objects in the catalogue. It's probably similar to the Milky Way in many ways, so it's a kind of a late-type spiral galaxy, forming stars at a rate comparable to the Milky Way, so about 2 solar masses per year. In other words, 2 stars of the Sun's mass are forming every year in M74. And so because it's forming stars, the young stars, the massive stars that are being formed, have a fairly limited shelf life, typically tens of millions of years. So, for example, M74 has had 2 core collapse supernovae in the last decade.
Here you can feed the exposure time, give a name for the file, and make several exposures of this target. For this object, well, I think that it will be interesting to use a R filter.
And that's red light?
Yeah, it's red. Of course, the ideal filter will be the H-alpha, but the H-alpha is very narrow and you have to take much more exposure time, no?
And we don't have time tonight. We're just doing a very quick one before you do your real work.
So make something like 1 exposure of 2 minutes, M74, let's do a glance and run.
That's that simple.
So simple as this.
Supernovae are kind of super bright events. Historically, amateurs used to find them. They were seeing what appeared to be a new star, but in fact it kind of signalled the death or demise of a star system. What's happened is that now we have all-sky surveys with basically the large telescopes from the ground, and so the professionals are now taking repeated images of the same or large bits of sky, and again using algorithms rather than using their eye to actually find changes. If we go back 50 years, there were maybe 10 supernovae discovered in that particular year, 1962. Whereas now we're looking at, because of the combination of the advances in terms of technology for kit for amateurs and in terms of the all-sky surveys for professionals, I just checked that in 2011 there was like 300 supernovae found.
So now we have to wait 2 minutes?
Yes, we have exposed 2 minutes and then we have wait 1 minute more to read the image and save the file.
This is part of your job, is it? Just waiting and waiting?
Well, yes. If we want to acquire some photons, we have to wait to catch them in the detector.
Some of the work I do is actually taking images of galaxies and then waiting for then the supernova to go off, hoping in the next lifetime of an astronomer that supernova goes off and we can actually then look at what was there before the supernova actually blew up, which star blew up. Because M74 is pretty close, even though it's 30 million light years away, it sounds like a lot, and it is a lot, it's actually relatively close by in terms of supernovae. So in fact, of the 2 that have gone off, one of them's pretty well studied. It's what we call a type 2 supernova, which is basically a supernova going off when its envelope is hydrogen-rich. And the thing that produced the 2003 supernova was probably what we call a red supergiant. Betelgeuse in the Orion constellation is one of the most famous examples of a red supergiant. These things are kind of really big bloated stars, and these are the kind of most common cold collapse supernovae. But the other supernova in M74 that went off in 2002, that was a more unusual type. It's a type 1c. Type 1 means there's no hydrogen. So something's caused that hydrogen to be peeled away from that star. And it can either happen because the star is very massive and then loses a wind and all that hydrogen just gets blown away before the star dies, or it can be in a binary system where the companion loses its hydrogen envelope and basically gets accreted onto the companion star and then it blows up without the hydrogen surrounding stuff, and it's a helium star basically blowing up. We didn't see the progenitor, and that means we can't say for sure which of these 2 scenarios was the one that produced it.
It just changed to orange. Does that mean it's nearly finished?
Yeah, it's nearly finished. Now we can do this command, display S1, the name of the file name, and the chip, we can see here the chip number 4, that is the central chip of the CCD.
You got it.
Yeah.
That's it.
Here is the bulge of the galaxy, the central region, and these are the arms. The halo of the galaxy extends much more, no? You are seeing something like the 20% of the galaxy. The 100% is extended several arc minutes, no, from the center.
This is part of the data I took to actually look for the progenitors of these future supernovae of a certain type, the ones that lose all their wind. So now I can know that if anything else happens in this galaxy in the near future, I'll be able to look as to where that went off and see whether I could see this kind of types of stars I can study to see whether it was the genuine star that blew up producing that type of supernova. The thing is, we know that these things are forming stars at a fairly high rate, which means that there's going to be thousands of these types of stars in that galaxy. So it may be that in this one galaxy, nothing happens for another 100 years, and that's very bad for me because I'll be dead. But what it does mean is that if you can survey enough galaxies, it's likely that over a lifetime of an astronomer, something's going to happen.